Hi, this is the continuation of our lecture on quadrilaterals. Last time we had covered numerous theorems related to the properties of parallelograms. This time we'll look at a couple more properties or theorems related to parallelograms, and then we'll move on to something called the midpoint theorem. So, theorem number 8, a quadrilateral is a parallelogram if a pair of opposite sides is equal and parallel. So, consider any quadrilateral. Let's name it A, B, C, D, and we have to prove that if a pair of opposite sides is equal and parallel, say AB is equal to CD, AB is equal to CD, as well as AB parallel to CD, CD, prove that ABCD is a parallelogram. This is a shorthand for parallelogram. So let's see how we can go about doing this. Let's start off by drawing the diagonal. Let's say diagonal DB. Then, because AB is parallel to DC, AB parallel to DC, and with DB as the transversal, we have angle ABD is equal to angle BDC. Angle ABD is equal to angle BDC. Why? Because these two are internal alternate angles. So AB is the parallel line and the line segment BD is the transversal. And so by SAS congruence rule, we have triangle ABD being congruent to triangle CDD, and hence from this we can see by CPCT that BC is equal to DA, BC is equal to AD or DA. So we have proved that BC is equal to AD. So we have proved this is equal to this, and also by CPCT we have angle ADB is equal to angle CBD. Angle ADB is equal to CBD, and so therefore this angle is equal to this angle. And considering AD and BC to be a set of lines and this to be BD to be the transversal, if these two angles were equal, this would imply that AD is parallel to BC, and in fact they are. And so therefore AD is actually parallel to BC. So we have proved that the opposite sides are parallel and equal if we are given that the other set of opposite sides are parallel and equal. And so therefore theorem 8 has been proved. Right? Now we move on to a very important theorem called the midpoint theorem. The statement goes as such: the line segment joining the midpoint of two sides of a triangle is parallel to the third side. Let's see how this looks like geometrically. Draw a triangle first. Say this is A, B, C. The line segment joining the midpoints of two sides of a triangle is parallel to the third side. So say this is the midpoint and this is the midpoint. So let's call this point D and let's call this point E, somewhere here. So if you join this to prove DE is parallel to DC, that is what we have to prove. Let's see how we can do this. We'll start off with a construction. extend a ray from point B which is parallel to AC. This ray is parallel to AC. Then let's call this F, point F for simplicity. This is a random point here. And extend DE to meet this ray, right? And call this, say, point G. So we have AC parallel to BF by construction. Now these two are vertically opposite angles, and so therefore we can say that on considering AC parallel to BF and transversal AB, we get angle DAB, angle DAB or angle DAE is equal to angle EBG. So this angle is equal to this angle, and also because E is the midpoint of AB, we have this side is equal to this side. Now, so obviously this side is equal to this side. So AE is equal to EB. Now by ASA congruence rule, we have triangle AED is congruent to triangle BEG. This implies by CPCT we get AD is equal to BG. AD is equal to BG, right? And we know that these two sides are also parallel. That is, we know that DC is parallel to GB. And please note that AD is equal to DC. This implies DC is equal to GB. Now in DGBC, DC is equal to and parallel to GB. This implies DGBC DGBC is a parallelogram. This implies DG is parallel to CB, and we'll continue here. So we have DG parallel to CB, and so therefore we have DE parallel to BC. Hence proved. This is what we started off to prove. Right. Another important consequence of this would be that again by CPCT, this is the congruency condition, we have DE is equal to EG. DE is equal to EG. Right. So this side, this is equal to this, and so therefore because DGBC is a parallelogram, DG is equal to BC, and so therefore 2DE, that is by writing DG is equal to DE plus EG and replacing EG by DE, we get 2DE is equal to BC. This implies BC is equal to 2DE, or DE is equal to half of BC. Another important part, which is not an explicit part of the theorem but a very important result, DE is half of BC. Another important theorem is basically the converse of the last theorem, which is the line drawn through the midpoint of one side of a triangle parallel to another side bisects the third side. Again, the proof is pretty elementary and can be done very easily using congruent triangles. The proof is being left out here as an exercise. This is all we have to say insofar as quadrilaterals are concerned. For now, this is all. Thank you.